This is a little biochemistry tutorial on exponents, scientific notations, and logs. In biochemistry, in science, we tend to deal with very large and very small numbers. And sometimes that can just be a little bit laborious to write out those long numbers. So for instance, we might be looking at Avogadro's number, or the weight of an atom, or the concentration and the molar concentration of some molecule in a cell. And so sometimes those numbers, again, are very big and very small, and writing them out like this can become a little annoying over time. And so we've got this process where we can actually put it into scientific notation. And so let me show you that process first. This number, for instance, we're going to convert to scientific notation. And to do that, the decimal point, realize, is right out here on the right hand side. And so in scientific notation, what we're going to do is try to change this number into a number that looks like 4.2 times, and we times it by 10 to the exponent, and the exponent is indicative of how many spaces we have to move the decimal point to get this number that I've written out right here to look like 4.2. So to do that, I'm going to move this decimal point over 1, 2, 3, 4, 5, 6, 7, and 8. And so by moving over 8 spots, I can then write the exponent here in this number to the 8th, meaning I've moved the decimal point over 8 spots, and now I have this number 4.2. This is a much more concise and efficient way to write the number that I've written above. They both are the exact same number, it's just one is in scientific notation, the one I have boxed. So to give you just another example of one of these, let's see, 0. So here's another number. Again, it's a small number this time as opposed to a big number we had the first time. But again, I'm going to convert this into scientific notation, so I'm going to make this number look like 3.3, and then we'll multiply it by 10 to the number of spaces we have to move the decimal point. So this time we're going to move the decimal point to make it look like 3.3. I'm going to move the decimal point over 1, 2, 3, 4, 5 spots. This time, because we move the decimal point to the right, it's not a positive 5, it's a negative 5. So the negative is indicative of this is a small number, we move the decimal point over to the right. In the above example, at the top, where we had 4.2 times 10 to the 8th, that's a big number, it's greater than 1. We moved the decimal point to the left, so therefore it was a positive 10 to the positive 8, as opposed to 3.3 times 10 to the minus 5, telling us it's a small number that we are denoting in scientific notation. So the two boxed numbers are scientific notation. Now, one note that I'm going to make here is some of the shorthand notation we use sometimes with numbers like this. So let's write this number into scientific notation. So I'm going to make this number look like a 1. And so how many decimal, or how many spots do I have to move the decimal point? I have to move the decimal point 1, 2, 3, 4 spots. So it'll be 1 times 10. And since we move the number to the right, i.e. we have a very small number to begin with, it's going to be a negative. And since I moved it 4 spots, it's a negative 4. And so this in scientific notation would be 1 times 10 to the minus 4. Sometimes, though, and maybe not in a way that's a little bit lazy, you see that we can remove the 1 times as it would be understood and just write 10 to the minus 4. 10 to the minus 4 is identical to 1 times 10 to the minus 4. It is just a way to write it in a very simple way because the 1 is understood. Similar to if I have x plus 7 equals 10, it's understood that it's 1x. I don't have to put the number 1 in front of the x to indicate that it's a 1x. It's understood to be 1, and so we can just leave the 1 out and just be left with the number x plus 7 equals 10, and we can solve for x in that way. So just like that, we can also write it just 10 to the minus 4, and that means 1 times 10 to the minus 4 as a shorthand notation. Okay, so let's practice this just really quickly. I have 5 problems up there. If you want to convert that, if you want to pause the video, convert these into scientific notation, and then when you're done, if you restart the video, I will go through the mental explanation of how I would answer that problem. So pause the video and go ahead and give these a try. Okay, the first one, let's convert it into scientific notation. So equivalent to that is I'm going to write this number as 2.43. So how to get this number on the left to look like 2.43? I have to move the decimal point over 1, 2, 3, 4, 5. If I move that decimal point over 5 slots, I can use the number 2.43 times 10 to the 5th, and that's a positive 5 because I have a very big number here. 243,000 is greater than 1, and so it's a positive 5 because I moved that decimal point to the left to make that number. On the second one, I'll do a similar thing, except I'm going to convert it into a 1 to write it in scientific notation. So to do that, here's my decimal point out here, and I move it 1, 2, 3, 4, 5, 6 spots. So that's 10 to the 6th. So that's completely fine. That's scientific notation, 1 times 10 to the 6th. That's equivalent to the number I have on the left, which is 1 million. But realize I can even write this even more efficiently and just call it 10 to the 6th because the 1 times is understood. Notice I can't do that with the first one because 2.43 would not be understood. You can't just write the first one as 10 to the 5th. That's not a fair, you can't do that. On the third example, I'm going to try to make that a 1 as well. So 1 times, to make it a 1, I got to move this decimal point over 1, 2, 3 spots, and that'll make it look like a 1. So moving it 3 spots, I have to go times 10. In this case, it is negative 3 because I have a very small number I'm starting with, and I move that decimal point over to the right. So when you have negatives in the exponent, like negative 3 here, that means you're working with a smaller number, meaning less than 1. And again, I can write this a little bit more efficiently because the 1 times would be understood, so this is fine to write as 10 to the minus 3. On the third one, seems tricky, but if you do the same thing you've been doing all along, you'll get the correct answer. So in this case, I'm going to make this look like a 1, so times. The decimal point is right there, so I don't even have to move the decimal point to make it look like a 1. So 1 times 10 to the 0, because 0 meaning I didn't move the decimal point, and so that's scientific notation for a 1. And I can write that even more efficiently by calling it 10 to the 0, but to me more efficiently is just writing it as 1. But nonetheless, that would be the proper scientific notation. 0 meaning I don't even move the decimal point. And then the final one is the last one. In that one, I'm going to make it look like a 4.4. I have a very small number here compared to 1, and so I have to move this decimal point 1, 2, 3 spots. Whoops, sorry about that. I don't want to move it that far. I want to make it look like 4.4 is what I set out to do. And so there it is. I have to move it over 1, 2, 3 spots. And so it's 4.4 times 10 to the negative 3 because I moved the decimal point to the right. And again, when you see the negative, it just means it's a smaller number. I can't make that any more efficient. I can't get rid of the 4.4 and just write 10 to the minus 3. That wouldn't be fair. And so therefore, that would be the correct notation. So let's do some mathematical calculations using exponents. And you can do this without a calculator by just knowing the rules of multiplying and dividing numbers with exponents. And so let's do this one first. And so I'm going to multiply 10 to the 4th times 10 to the 6th, and then divide it by 10 to the 5th. Anytime you multiply exponent numbers like this, you just add them together. Anytime you divide, you subtract them. So in this case, I have 10 to the 4th times 10 to the 6th. So really what I'm going to do in my head is add 4 plus 6, because I'm multiplying here. Whoops. Sorry about that. Let me get rid of that and try this again. So I'm going to put it down a little lower. I'm going to just add 4 plus 6 together, which equals 10. And so on the numerator, to multiply 10 to the 4th times 10 to the 6th, I just add 4 and 6, and I get 10 to the 10th over 10 to the 5th. And then for the second part, to finish out the division here, I will do a subtraction of the numerator minus the denominator, which in this case would be 10 minus 5, which is 5, and so I get 10 to the 5th as an answer. And so you can see without a calculator I can multiply and divide exponent numbers. Now let's take a look at a second problem. In this problem it's not as easy as just adding the exponents, although you can kind of do that. It's a little bit more difficult. So a problem like this that I show down here would require a calculator. I wouldn't expect you to be able to do this in your head, although it's possible. We'll leave that to other people. This would require a calculator. The only time we can really use our trick of adding and dividing that we'll be seeing is when we have equations like this, where it's 1 times 10 to the 4th and 1 times 10 to the 6th. Other than that, you have a little bit more calculation to do, and that starts to becoming out of the scope of what we're going to do in our head. So here are a couple practice problems for you. Go ahead and try these out. Pause the video, try these out, and then when you're ready, when you got the answers, come back and then I will go through the mental thought process of calculating these two mathematical equations using exponents. Okay, so let's take the first one. We're doing a division of 10 to the 8th divided by 10 to the 4th. So in this case, since we are dividing exponents, we need to subtract the two exponent values. So in this case, the numerator is 8 minus 4 equals 4. So the new exponent will be a 4. And so in this case, the answer to this is 10 to the 4th. In the second problem, we have a couple of calculations to do. We've got to multiply 10 to the negative 3 times 10 to the negative 2 and divide that by 10 to the negative 4 times 10 to the negative 3. So what I'm going to do is multiply the numerator by itself and multiply the denominator by itself first. So anytime we multiply, we can just add the exponents. So in this case, on the top, on the numerator, it's going to be minus 3 plus a minus 2. So a minus 3 plus a minus 2 is a minus 5. Whoops, sorry about that. Minus 5. And so in this case, in the numerator, I have 10 to the minus 5. In the denominator, I have minus 4. I'm multiplying it times 10 to the minus 3, so it's going to be plus a minus 3. A minus 4 plus a minus 3 is a minus 7. So the denominator will be 10 to the minus 7. And now we can divide these two, and when we divide these two, we subtract the exponents. So in this case, it's going to be minus 5 minus a minus 7 equals a minus 5 plus 7, because the two negatives will delete each other, essentially, nullify each other, and so minus 5 plus 7 is 2. And so the answer to this is 10 to the 2 is the answer to the second problem. So there is using mathematical calculations with exponents, which will help us when we get to the next part. So now let's start talking about logs a little bit. Let's say I gave you this problem, 100 equals 10 to the x. And I asked you, what is x in this case? Now you might be able to look at this now based on our previous discussion and what you know about exponents. You might be able to figure out what x is. But remember, x in this problem is how many spaces do I move the decimal point to make it look like a 1? Because remember, this is 1 times 10 to the x. And it's that 1 that we're trying to make it look like. So when I see 10 to the x, I'm trying to make this number on the left, this 100, look like that, and the x is how many spaces do I move the decimal point. And we all know now if I take this and move this over 2 spaces, I will get 1. And so x in this case is 2. By doing that, you actually just did a log. Log is this. If we take the x value, so we say, and remember x is how many spaces do I move the decimal point to make it look like a 1. X equals log base 10 times 100 is the actual calculation you would do on your calculator to get this answer. This above, how would you calculate that? Well, you'd calculate by converting it or doing the equation of this log. This is the way you would do it, because some numbers aren't as clear-cut as the one I just gave you above. But in this course, this is what we're going to see. And we're going to deal with logs a lot because there's equations that we deal with that have logs in them. And so when you see this, all this log equation is asking you is, how many decimal points do I have to move to make that number, that 100, a 1? And you can see, as we already know, we move the decimal point over 2, and it's a positive 2 because it's a big number, and we're moving that decimal point to the left. And so the answer here is x equals 2. In this case, we move it over 2 decimal points. So that's what we need to be able to do with logs for this course. So here's a question you can try. This would be a reasonable question. What is the log of 10,000? So take a moment and come up with that answer, and then we'll talk about it. Okay, so if I were to set it up in an equation format, which you don't have to do here, but if you did, you would say x, how many spaces do I have to move that decimal point to make that 10,000 look like a 1, equals the log base 10 of 10,000. That's what the way the equation would look. And if you had this on your calculator, and you can do this, you can type in 10,000 on your calculator, hit the log button, and it should come up with the answer for you. So you can actually practice this on your calculator, and your calculator will give away the answer. But we can do this without the calculator because we now understand this whole decimal moving. 1, so the decimal point's out here, so I move over 1, 2, 3, 4 spots. So in this case, 4 equals the log base 10 of 10,000. So we can convert the log base 10 of 10,000, and that number is 4. So let's now move a little bit more into biochemical systems. Let's talk about pH. pH means the H stands for the hydrogen ion concentration, or H+. And that's and concentration, remember, is used by those brackets. So that bracketed H+ means concentration of H+. P means, basically it means negative, for our use, it means negative log is what the P part means. And so pH really stands for negative log of H+. So that's what pH stands for in a mathematical way. So it actually is it's very related to the concentration of the hydrogen ion. And so if I wanted to know what is the hydrogen ion concentration, similar to the assessment quiz, if I want to know the hydrogen ion concentration of pH at 8, or in this case, let's do what is the hydrogen ion concentration for pH equal to 6.0, let's say. What I'm asking you is the negative log concentration of hydrogen equals 6.0, or 6, really. We don't even need the 0.0 on that. So that's what I'm asking you. And remember, this looks a lot like x equals log of some base 10 of some value. We'll call it y. We had 100 in there, or 10,000 in there, or something like that. You see how these two equations look very similar. So what the 6 is the number of decimal places I have to move to get the value. So let's do this equation now. Let's go ahead and determine the hydrogen ion concentration, thinking about logs. Okay. Let me get rid of that old markings, and we're going to do it. So the first thing is I'm going to get rid of this negative out here where it says negative log. I'm going to get rid of that negative. And I'm going to do that by multiplying both sides by -1. So by doing that, this becomes positive on this side. H plus equals -6. And I'll just get rid of the 0.0. It doesn't matter. So what it's saying is I need to move the decimal point over 6 spots to the negative direction. That means that this number for hydrogen, I now know. It's 0 because it's -6. It's 0.0000006. Notice if I move this decimal point over 1, 2, 3, 4, 5, 6. Oh, I'm sorry, that's not 6, that's 1. It's 6 decimal points. It's not the number 6, that's a 1. What that means is I just moved the, just to check myself, I moved the decimal point over 6 spots, and sure enough, I got 1. And so what this means is the hydrogen ion concentration is this. And that is actually in molarities. So it's in M because we already know it's hydrogen ion concentration. That's shown in molar. So the hydrogen ion concentration at a pH of 6 is 0.000001. And that's just done by this equation because pH stands for the negative log of the hydrogen ion concentration. So let's do one more problem. And this is basically the end of it. Once you understand this, I think you got it. Let's do this calculation. Let's determine the log base 10 of 10 to the minus 2 times 10 to the minus 4 over 10 to the minus 3 times 10 to the minus 3. And let's see if you can determine that. So pause the video, do the calculation, then come back and I'll talk you through it. Okay, so the first thing I'm going to do is simplify what's in that parentheses here, this 10 to the minus 2 times 10 to the minus 4 over 10 to the minus 3 times 10 to the minus 3. And I'll first do the numerator. So the numerator has 10 to the minus 2 times 10 to the minus 4. Remember, when we're multiplying exponents, we add them together. So minus 2 plus minus 4 is minus 6. So minus 6 will be in the numerator. The denominator is going to be 10 to the minus 3 plus 10 to the minus, or 10 to the minus 3 times 10 to the minus 3. So I add the two negative 3's together. And it turns out that that comes to 10 to the minus 6 as well. Okay, so that's what we have so far. And remember, this whole log base 10 is still there. And I can still calculate x. So now let's take 10 to the minus 6 divided by 10 to the minus 6. And let's go ahead and do that division. Remember, what we're going to do is, because we're dividing, we're going to subtract the 2. That's minus 6 minus a minus 6, which is the same thing as minus 6 plus 6, which equals 0. And so in this case, this guy reduces to 10 to the 0 is log base 10 of 10 to the 0 equals x. So remember, 10 to the 0 means I'm going to move the decimal point, no spaces, to get to 1. And so this whole thing, this whole log base 10 of 10 to the 0, and I'll put these in parentheses just to separate that out so we can see it. Remember, 10 to the 0 is actually the log base 10 of 10 to the... So 10 to the 0 is 1. So we have log base 10 of 1 equals x. And then remember, to solve this, what we're asking, remember what x is how many places do I have to move the decimal point to make the number look like a 1? The number already looks like a 1 right here. And so I don't have to move it any spaces. And so in this case, x equals 0.